Hi everyone, this is Dr. Doherty in beautiful Abilene, Texas, talking today about energy. Energy is the most important concept in all of physics, probably even all of science. I want to make this really clear that the way that we actually solve physics problems in the real world is to think about energy. And the farther you get into physics, the more important energy becomes. It is the thing that really matters. It's way more important than the big four kinematics equations. It's more important than Newton's laws. Energy is the most important idea. Pay attention to this. So there's a lot of new concepts we have to talk about, a lot of things to juggle. So I'm going to keep this as short and simple as possible because I've got three ideas that all relate very tightly together. And when we get to the end, all of this should fit very nicely. So let's try to keep this as short and simple and direct as possible. So when I have an object and I want to give it energy, the word for this in physics is work. When I do work to an object, I'm giving another object some of my energy. And the way that we do this is by pushing or pulling stuff around. So work is going to depend on things like force and distance. So I'm pushing it. How hard am I pushing it? How long do I push it for? Okay, so that gives us a simple definition of work then. The work done by a constant force is the force F times the displacement times the cosine of the angle between these vectors. So F and S here are the magnitudes of the force and the displacement vector, and then cosine theta is the angle between these. If you're comfortable with math, you might recognize that this is just a dot product between F and S. Now I get simple units here. I get units of newtons times meters. Remember that cosine theta is dimensionless. And we're going to call this combination of a newton meter 1 joule, named after this guy, who was the first person who converted mechanical power into heat. We'll talk more about him in a little bit. Okay, so if I do a force applied for a distance, we're going to call that work, and that has units of energy, which are joules. Now notice this cosine theta. Normally we're going to have situations where this becomes really easy. If F and S point in the same direction, cosine of 0 degrees is 1, so the work is just equal to F times S. If the cosine of theta is 90 degrees, cosine of that is 0, and the work is 0. So if I'm going to be pushing an object to the right, but it's going up, I'm not helping that object move. I'm not actually doing any work there. Similarly, if the cosine of my angle is negative because of my cosine is 180 degrees, if it's trying to move up but I'm pushing it down, I'm actually fighting its motion. My force is going the wrong way. So the work I'm going to be doing is negative. So if I'm helping it move, my work is positive. If I'm neither helping nor hurting, that is, I'm pushing sideways, my work is 0. And if I'm opposing the motion by pushing backwards, the work is going to be negative. Now, since we talked about joules, let's get a feel for how big this is. Whenever you see a new unit, it is so important to get a feel for what it means so you know if your final answer makes sense or not. So here's a quick guide. 1 joule, that is one of these guys, pushing a cantaloupe across a desk. 1,000 joules, or 1 kilojoule, bench pressing 400 pounds. A megajoule is going to be pushing a car for a kilometer, or a gigajoule, 1 billion joules, driving a car for a month. So know that your answer should make sense with something on this scale. So now let's define a new thing, kinetic energy. We've talked about this word kinetics and kinematics and cinema, all have to do with motion. So if I have an object that's mass m moving at speed v, the kinetic energy is 1/2 mv squared. Now this also has units of joules. A kilogram meter squared per second squared is the same as a Newton meter. And the nice thing about this then is that work changes an object's kinetic energy. This usually has the really helpful name of the work energy theorem. So let's think about this. I've got an airplane. Its initial kinetic energy is 1/2 mv squared. We push it for some distance, so now its final kinetic energy is 1/2 mv squared for something else. If I do positive work, this delta kinetic energy, remember that's always final minus initial, my change in kinetic energy is positive. So if I do positive work, you speed up. If I do negative work, you slow down. And if I do zero work, I don't change your kinetic energy, which is that I don't change your speed at all. So keep these concepts together. It's really handy. So now let's add the third thing to the mix. Let's talk about gravity. So work can be done by any force. If I have lots of forces going on, I could even say the net force is doing some work. So now let's talk about the work done by a single force of gravity. So I've got a basketball here. It's going to fall some height h. So here's my displacement going from my initial height h down to 0. My force is mg pointing downwards. So the work is F times S cosine theta. It's a definition from before. My force and my displacement point in the same direction. So my theta is 0 degrees. Cosine of that is 1. My force is mg in the downward direction. My displacement is the height. So I start at height h, I end at height 0. So my distance here is h. So then the work that gravity does in making something fall is mgh. Now remember, positive work makes kinetic energy increase. When gravity makes something fall, it speeds up. So positive work, positive change in kinetic energy. So now let's define a new kind of energy based on that idea. This is going to be gravitational potential energy, mgh, just like before. Now this is going to be defined as the amount of energy an object has based on its ability to fall, its ability for gravity to do work on it. Now remember, this has units of energy, just like work, just like kinetic energy. It's the energy I get by being above the Earth's surface. But one interesting thing here, this height h is relative to some arbitrary level. I can define my h relative to sea level, or relative to the local ground, or the second floor of the science building, or my shoes, or the Earth's atmosphere. It doesn't matter, as long as I'm consistent, because what matters is the work done over a change, over some change in height, over some distance. So I can define my energy relative to whatever I want. Let's put the pieces together. I've got an object with a mass of 0.1 kilograms. So its weight, mg, is going to be about 1 newton. Now gravity is going to do mgh, that's about 1 newton times h, or about 1 joule of work for every meter that it falls. So let's have a ball here that starts at rest 3 meters high. Now my potential energy, mgh, mg is 1, h is 3. My potential energy here is 3 joules, and at 2 meters high it's 2 joules, and at 1 meter high it's 1 joule, and at 0 it's 0. That's my potential energy. That's what I'm starting with. Now my kinetic energy starts at 0 because my ball starts at rest. Now when I fall for 1 meter, gravity does 1 joule of work. The work energy theorem says that work is a change in kinetic energy. So if gravity does 1 joule of work, its kinetic energy is now 1 joule. When it falls down here to the 1 meter mark, it's fallen 2 meters. Gravity's done 2 joules of work. So it now has 2 joules of kinetic energy. And at the bottom, it's got 3 joules of kinetic energy. Now notice what's happening here. This is the key idea in this section. When I fall, I lose potential and I gain kinetic, but my total energy is constant. I started with 3 joules and I end up with 3 joules. What happens is it's the work done by gravity that's transferring potential energy to kinetic energy. So as I fall, gravity does work, which makes my object speed up, and for every joule of potential it loses, it gains exactly 1 joule of kinetic. And if you understand that, you know what you need to know about energy. So, let's go through the whole idea, just to make sure we're all on the same page. All objects have energy stored in many different ways. Kinetic energy, if they're moving, and there's lots of kinds of potential. We've talked about gravitational potential, but there are other ways to store energy. I could compress a spring. I could take two positive charges and mash them together. There's lots of ways to do it. As the object moves, it can convert one form of energy to another. It can go from kinetic to gravitational potential, or potential to kinetic. But the total energy needs to be constant. Now, this transfer from one form to another or one object to another is what we call work. I want to give the object energy, I do work on it. Well, so if I do 1 joule of work on something, where does that joule come from? Well, I guess it came from my chemical potential energy from all that coffee that I just drank earlier. Similarly, an object can lose energy by doing work on something else. So where did this come from? Well, the first recorded case came from this guy, Julius Robert Van Meyer, who was expelled from college in 1837. So, as you do when you get expelled, he and his buds took a road trip, or I guess a boat trip, over to Indonesia. He had such a good time, he comes back a few years later as the ship's doctor, because remember, back then you can be expelled from college and still be a doctor. He noticed that his patient's blood was a deeper red in Indonesia than in Germany. So he is the first recorded person in history to write down this idea that energy can neither be created nor destroyed. So an object can't spontaneously gain or lose energy on its own. It has to come from somewhere. If an object has 10 joules of potential energy, that came from somewhere. Something pushed it. If an object has 10 joules of kinetic energy, that came from somewhere. A book sitting on your desk can't suddenly take off and get kinetic energy on its own, which is a really good thing because that would be weird and frightening and really dangerous. Energy can only be transferred through work from one object to another or one form of energy to another form of energy. The universe apparently has some fixed amount of energy. We can't make more, we can't get rid of any. Energy is conserved. And this idea of the conservation of energy is the most important idea in all of physics. Now, why do we call it a joule then instead of a Meyer? Well, in 1843, James Joule independently did the math to show this conversion from one form to another. His experiment's really simple. We have a weight on a pulley, and the string here is wrapped around some little rotor that spins around in a coffee can full of water, and the thermometer measures the temperature in the coffee can. And what he finds is that if this weight falls, it loses potential energy, and for every unit of energy that it loses here, that gets converted into heat in the water. His actual setup really did look like a coffee can with a little stick and a string. And so this is why we call this the Joule, named after his work. So, when we have a problem to solve, all we have to do is write down the initial energy and the final energy, because those things have to be the same because the energy is conserved. And that's such a powerful tool for solving problems. Most physics problems are solved by looking at energy. So, one final example to make sure that we're good on the concept. When I take an object like this bobsled, I define the total energy as kinetic plus potential. So my bobsled here starts at rest, 0 joules of kinetic, 600,000 joules of potential, 600,000 joules of energy. Now by the time it gets to the bottom, because of conservation of energy, the initial and the final are the same, so it still has 600,000 joules. And in fact, everywhere as it's falling, it still has 600,000 joules of total energy. But I go from all potential to all kinetic. And I can use that to find out a lot of interesting things like how fast is it going? So here's a great example of how this kind of works out. And this is actually really practical theme park physics. We do this at Six Flags a lot. If I take this ride, the King to Ka, with a vertical drop of 127 meters, if the speed is 6 at the top, find the speed at the bottom, where it's got 0 potential. Okay, every one of these problems, initial energy equals final energy. Okay, so what do I have? I'm going to have gravitational potential, and I'm going to have kinetic. So my final potential plus my final kinetic equals my initial potential plus my initial kinetic. Now for gravitational potential, I could very easily set its initial height to 0 because that's relative to some arbitrary thing and I can always change it however I want. I'll usually have a kinetic term here have a 0 velocity somewhere, but not this time. It's going 6 at the top and we don't know how fast it is at the bottom. So my masses cancel. They almost always do in these problems. I'm going to solve for what's my final velocity in terms of my heights and my initial velocity. So I do that, I get this equation. It looks a little ugly, but it's not bad. It's actually really similar to what we've done with the big 4 equations. My final velocity is the square root of 2g times the change in heights plus my initial velocity squared. Okay, I plug in some numbers. My change in height was 127 meters. By the way, if you're worried about signs here, remember that when I fall, I should be gaining velocity, so I need to have positive numbers here. Plus my initial speed squared equals about 110 miles per hour. As always, the final question you ask is that a reasonable speed for a roller coaster? Yeah, it is. It's a little fast, but remember, we've neglected things like friction and air resistance, so the real answer is going to be a little bit slower than that. Okay, I know this looks ugly, but remember, every one of these problems is exactly the same. Initial energy equals final energy, so all these problems look similar. And doing it this way really is so much easier than trying to find the force and the acceleration and using the big 4 equations to find a final speed. Final review. We talked about 3 important things. Work, that's force times displacement times cosine theta. That's how we change energy from one object to another or one form to another. Now work changes kinetic energy. So work is the change in kinetic, W equals delta KE, and gravitational potential, mgh. Now these 3 things are very, very closely related because energy is conserved. So remember, when an object falls, gravity does 1 joule of work to lose a joule of gravitational potential to gain a joule of kinetic. Work transfers from potential to kinetic energy. Every problem here is solved by conservation. Initial energy equals final energy. Now you might have some annoying problems where there's a non-conservative force like friction that's causing energy to leak out of your system into something else. In that case, you just account for that, saying your final energy is a little bit less than your initial. But normally physics homework problems are nice, if a bit unrealistic, and we ignore all those annoying details. So, a lot of ideas to think about, but everything relates to each other. Balance potential and kinetic energy through work, and you'll get the answer right every time.